The part of physics that deals with the motion of objects is called kinematics. In this section, we will focus on the kinematics in one dimension. In other words, we will focus on motion that happens along a line. We start with the concept of displacement and distance. Both are measured in meters, but they're different. They're both related to the position or the change in the position, but the displacement is defined as the difference between the final and the initial position. In other words, mathematically, I will write it as a difference between the final position xf and the initial position xi. The distance, on the other hand, is defined as the length of the actual path that has been traveled by the object. Sometimes they're the same, sometimes they're different. Let me show you three very common scenarios that you might encounter in the introductory physics. The first one is for an object that is moving along a straight line, and it hasn't stopped, it hasn't gone back, no zigging, zagging, going in circles, just a plain straight line. For that type of motion, the displacement will be always equivalent to the distance. On the other hand, if the object has stopped and has already moved backwards, we will see that the distance is the length of the path traveled there and back, but the displacement depends only on the final and the initial position, so it will be a different value. The third most common scenario that you will encounter in the introductory physics will be objects moving along a circle. For that, it's very handy to use the geometrical formula for the circumference of a circle, which is 2 pi r. Very frequently, that will be our distance. If the object makes 2 rounds, that will be 2 times the circumference, or 3 times. But we start with the basic distance of that equal to the circumference of the circle. The velocity, which is measured in meters per second in physics, is defined as the change in the position over time. Or in other words, it tells us how fast the position or the displacement changes of an object. So we write that the average velocity is equal to the change of the position, which is the difference between the final and initial position, and the time. Mathematically, we will write this as delta x over delta t. We have another concept that is related to how fast things are moving, and that is called speed, also measured in meters per second, but it tells us how fast an object clears a distance. So here the average speed will be the distance traveled over the time. That formula is very handy frequently in situations where objects are moving along a circle. And so for circles, remember, we use the distance for one circle to be equal to the circumference of the circle. So I can write that the average speed will be equal to the circumference for one circle, 2 pi r, over the time for one circle, which in physics is called the period, marked as capital T and defined as the time for one circle or one revolution. So what about instantaneous velocity? In other words, what if we don't want average, but we want something that is now? Technically speaking, there is no such concept as instantaneous velocity in physics when you measure it. You will always measure some average value. But what you can do is when we average over a very small interval of time, that practically can serve the purpose of the instantaneous velocity. So we start with the formula delta x over delta t, and then we work with very small time intervals. Mathematically, the time interval has to be infinitely small, so this is how I have marked it, delta t going to 0. Physically, it doesn't have to be that small. It just have to be small enough in the context of your problem. Sometimes a millisecond is small enough, sometimes a microsecond. So you pick something very small and you average over that small interval. For those of you who are familiar with calculus, this becomes the definition of the derivative of the function x with respect to t. So in physics, you can say that the velocity is the derivative of the position with respect to t. Let's look at the instantaneous speed. Once again, we start with average speed, which is distance over time. And if you want to know the instantaneous speed, we're going to average over a very small time interval, and that will give us the speed at this interval, which for practical purposes, we will treat as if it's equivalent to the instantaneous speed. Here's a very important and interesting note. When you're working with very small time intervals, or when you're working with instantaneous quantities, you will find out that the displacement and the distance are always the same, with possible difference of one sign. In other words, the object, when you're working with a millisecond or microsecond or whatever is a small interval for the context of your problem, the object hasn't had the chance to deviate too much, going zig or zag, and so that the distance will still be close or equivalent to the displacement. The difference will be just a sign, because the distance is simply the length of the path, while the displacement keeps track of which end is the beginning and which end is the end of that motion. As a consequence, you will find out that when you're working with instantaneous concepts, the velocity, the instantaneous velocity, will always be equal to either plus or minus the value for the speed. Or mathematically, the way we write it in physics is that the absolute value of the velocity will be equal to the value for the instantaneous speed. What if the velocity changes? Well, when we have a change in the velocity, we need to work with the concept of acceleration, measured in meters per second squared. And acceleration is defined as a concept that tells us how fast the velocity changes. It is defined technically in the following manner. We start again with average acceleration, which will be equal to the ratio between the change in the velocity, final velocity minus initial, over the change in time, or the time interval. Or in short, I will write it as delta V over delta T. Compared to the velocity, the way we introduced it, velocity gave us how fast the position changed, and it was equal, the average velocity was defined as delta x over delta t. If we need to work with instantaneous acceleration, again, we will average over a very small time period, and we start with the average acceleration formula. We work with small period of time, and that will give us the instantaneous acceleration. In calculus terms, this will appear to be the derivative of the velocity with respect to time compared to the velocity, which in calculus terms turned out to be the derivative of the position with respect to time. There will be no calculus examples or examples that require calculus in this course, so I have included that just for continuity, so you can see how calculus is being used in physics and how it ties up with the concepts here. Whenever we look at objects, very frequently we will have a situation for which the object is moving with a constant acceleration. In other words, the velocity will be changing at a constant pace or a constant rate. To illustrate that, let's start with time equals 0 seconds, and at that instant, let's say the velocity of an object is 2.0 meters per second, and that object has an acceleration of plus 5.0 meters per second squared. In other words, the velocity of the object will be increasing by 5.0 meters per second every second. So that means that if you wait 1 second, and so that your time counter shows 1 second, then the velocity will be 2 plus the increase. So 1 second has elapsed. That means the increase of 5 meters per second every second has to be added to the 2.0 meters per second original velocity. So now we have the object moving at 7.0 meters per second. At t equal 2 seconds now, we have already the object moving at 7 meters per second, and we have to add another increase of 5.0, so that will give us 12.0 meters per second. Or you can actually count this from the very beginning, so we can actually start with our original velocity 2.0 and add 2 increases, because 2 seconds have elapsed since the 0 mark. So I'll have 5 times 2 gives me the same 12 meters per second. At time equal 3 seconds, so 3 seconds after I started looking at that motion, the velocity will be the 2.0 meters per second with the original velocity with which it started, and then I'll have to add 3 increases of 5.0 because of the 3 seconds. So I'll have 5 times 3, and so that gives me velocity 17.0 meters per second. If you see the pattern of these numbers, you can actually see why I can write now the formula for the velocity in this form. The velocity at any given instant will be equal to the velocity with which I started at the 0 seconds, v naught, I marked it here, plus a times the time that has elapsed, times the acceleration times the time. So let me write it here, and I'll call this equation 1. It turns out that we will have two more equations for objects that move at a constant acceleration. The fastest and most effective derivation of those formulas require the use of calculus. But this is beside the point. I'll give you the formulas directly because we will be using them many times. Equation 2 will give us the formula for the position, how it changes with respect to time. So we're going to have x will be equal to the position from where we start, x naught, plus v naught times the time that has elapsed, plus 1/2 of a delta t squared. Delta t, remember, is the time that has elapsed since we started counting. Equation 3 is actually an algebraic combination of equation 1 and equation 2. Frequently we have information about the velocity, position, and acceleration, but we don't have information about the time in a problem. So the equation 3 gives you a shortcut and saves you the effort to go through 1 and 2, substitute time, replace time, and express time from equation 1, substitute in equation 2, and get that relationship. So here's the relationship. V squared will always be equal to V naught squared plus 2a delta x. Now, writing those triangles for the time that has elapsed could be quite cumbersome, and I frankly tend to be lazy. And sometimes it's even more clear to drop, but you have to remember that I keep that implicit assumption that the t here refers to delta t, to the time that has elapsed. So with that note, I'd like to rewrite those three equations in a slightly simpler form, at least at first sight. So I'm going to write them as v is equal to v naught plus at, x is equal to x naught, v naught t plus 1/2 at squared, and v squared will be v naught squared plus 2a delta x. I chose to keep delta x here because delta x is the displacement, and we already have those in the equation 2 actually, that delta x stands for x minus x naught. So once again, I'll call those equations 1, 2, and 3. They're identical to the original set. They just look somewhat less cumbersome without those deltas. There's one very particular situation in which objects move at a constant acceleration, and that is when you drop an object and let it fall. It will travel in the gravitational field of the Earth, and many centuries ago Galileo demonstrated that those objects will be falling downwards with an acceleration that is constant and equal to 9.8 meters per second squared. If we can neglect the air resistance and any friction, and there are no other forces acting on the object and it's freely falling, we refer to that motion as free fall. Because it's so common and established, that value of 9.8 meters per second squared is frequently in physics marked as g. And the direction of the acceleration is always downwards towards the center of the Earth. So with that in mind, you can take equations 1, 2, and 3 and rewrite them in the context of free fall. So here is how they're gonna look. V will be equal to V naught minus gt. X, or frequently you'll probably call it y, because they tend to move in the vertical direction and we like to use y for vertical directions. So x will be equal to x naught plus v naught t minus 1/2 gt squared, and v squared will be v naught squared minus 2g delta x. Again, 1, 2, and 3 equations. It's very important to remember that g here stands for 9.8 meters per second squared. There are no minuses in the symbol of g, but I have explicitly written a minus sign here in the equations, all three equations, because I have already made my choice for the upward direction to be the positive direction. So what if an object is moving but not with a constant acceleration? Well, generally speaking, there is no way to avoid calculus in that case. We have to say that the acceleration is the derivative of the velocity with respect to time, and the reverse operation will be integration, so the change in the velocity will be an integral of a dt. Similarly, v was the derivative of x with respect to time, and so the change in the position will be the integral of v dt. I have not included examples in this course that require calculus to get the solution of the problem. So I'm again putting this out there for students who are familiar with calculus and would like to see where the calculus is in physics. There is one situation, however, where we can have variable acceleration and still we can get to the answer. This is when someone has already given us a graph and they plotted the acceleration versus time. So if someone gives you a graph and you have the acceleration versus time, if it's a variable acceleration, as long as that graph is actually comprised of straight segments, you can always determine that the change in the velocity of that object will always be equal to the area under the graph. So if you want to see how the velocity changes from 0 to 10 seconds, you're going to find out what the area under the graph is between 0 and 10 seconds, between 0 and 60, etc. But it has to be a graph that plots acceleration versus time. The second graph that you might see in the introductory physics is a graph that gives you the velocity versus time. And apart from the obvious reading, just as in the previous graph, you can always read. In this case here, you'll be reading velocity. You can actually calculate the slope at any given instant time of t, 10 seconds, 20 seconds, you name it. And the slope at that time will be the acceleration of that object. On the other hand, if you calculate the area between two times, it will give you the change in the position between two times. Or the way we say it in physics, the displacement of the object will be equal to the area under the graph. But the graph has to be velocity versus time. And the last graph that you're going to see at this level of physics is position versus time. And you can read the position, but you can also look at the slope of that graph, and that will always be equal to the velocity.